Welcome to Wales Tech Week 2021. Thank you to our partners. Enjoy the session.
Well, good afternoon. Thank you for bearing with the session throughout the day. This is the last of the sessions, and what we're going to talk about now is to try and talk through the academic expertise in industrial decarbonisation, and particularly to focus on the university support for industrial decarbonisation in Wales. So what we're looking to do is outline some of the research and innovation activities that the universities in Wales are conducting to support the development and the movement towards net zero industry. And in particular, we're going to highlight some of the work that's being conducted by Swansea University, Cardiff University and the University of South Wales in collaboration with industry partners. And particularly, we're going to focus in this session on some of the activities via some of the more significant projects, including Flexis, Flexis App, the RISE projects, and some of the other collaborative projects that are being conducted, and also discuss plans for ongoing engagement and decarbonisation, ongoing engagement with industry partners to decarbonise in Wales, and with the South Wales Industrial Cluster in particular. So I'm joined this afternoon by Professor Richard Marsh of Cardiff University, Professor Alan Guwy of the University of South Wales, and Professor Dave Worsley from Swansea University. Good afternoon to you all, and really I'm going to throw straight to Richard, if I might, to kick off the session. So,
okay, great stuff. Thanks very much, John. So what I'm going to be talking about today are the key challenges in industrial decarbonisation, and for that I'm going to look firstly at hydrogen and then next at alternative reductants. So my name is Richard Marsh. I've been working at Cardiff University for about 15 years now. I'm a professor of energy systems, and my background is in gas turbine combustion and solid material gasification, for which I'll talk a little bit about alternative reductants in industry, but we'll focus a little bit on iron and steel making. But before I do that, because I'm the first speaker in this session, I've been asked to give a little bit of an introduction to the Flexis project, and I'll just quickly describe what that is and how that fits in with some of the research that you're going to see herein. So Flexis stands for Flexible Integrated Energy Systems. It's a £24 million research operation, and it's here to look at energy systems research capability in Wales and build on some of the world-class capabilities that we have between the partner organisations. The project itself looks at some key research areas, which include renewable energy systems and power, which is the area that I work in, energy safety and carbon utilisation, which is out of Swansea University, high voltage, hydrogen energy, and Alan will be talking a little bit about hydrogen later on. Then there's some interesting work on risk research, which involves human factors in energy, so it's a fascinating area to look at. Then we've got some materials on power electronics, earth energy systems, and the whole thing is kind of tied together by looking at the industrial impact, which is led by Dr. Chris Williams, who was probably speaking earlier on today about the South Wales Industrial Cluster. So we can see that this really is a collaboration between academic excellence and, of course, the impact within industry. And the project itself has been running for about 5 years now. The first phase came to an end at the beginning of 2021. I've put up here on the screen some of the targets which have actually been exceeded. So there's been independent auditing, which has shown that the targets have been exceeded. So that's the original target was 50 enterprises for cooperation. About £26 million of research funding secured, which is a good return based on the 24 million investment, and then 86 researchers working in supported entities. So the whole project has been divided between the Western Wales and Valleys region and the Eastern Wales region. So the Flexis extension has been granted, which is fantastic news. And again, it's just another celebration of how well things have gone in the project, that this is going forward. So that will come to conclusion in 2023. And hopefully beyond that, there'll be some very valuable contributions made, and long may it continue. So with Flexis introduced, I'm just going to talk about what my particular interest is in industrial decarbonisation. So first of all, how do we use hydrogen as a source of heat and power in large scale and primary industries? And then I'm going to look at some chemical reductants. So how we actually take carbon intensive ingredients into primary and very large industries and convert those over to decarbonized feedstocks, which is quite a significant challenge actually, because this is kind of how we've done things for, literally for hundreds of years. All right, a little bit of background then. So in the figure here, I've got some data here which basically shows the global greenhouse gas emissions by sector. So this is all of the basket of greenhouse gases being emitted across the world, and you can see that over 3/4 of it is taken up by the production and usage of energy. And actually, when we look at industrial energy, we're talking of almost a quarter of that. So from around about the 12 o'clock to the 3 o'clock position, we're really encapsulating everything that's going to go on pretty much in this session and talk about the academic impact of that. So the good news is, from an academic point of view, lots of work to do, lots of things that need to be done. I'll focus just a little bit on iron and steel making, because that's something obviously of great relevance within South Wales and Wales as a whole. So iron and steel accounts for 2.6 gigatons of emissions per year. It's the biggest point source of CO2 and other greenhouse gases among the heavy industries. There's certainly an increased demand for steel as we go forward, and it's not just in recycling. We'll always need primary manufacture of steel because the damn stuff just corrodes away, so you'll always need to replace it. And if we stick to a business as usual case, we're looking at 65 gigatons of CO2 equivalent per year as we go forward in the future. So there's lots of potential here for decarbonisation, but there's lots of innovation that needs doing in the meantime. So this is where we get to the crux of the problem, you see. It's not about converting these industries into renewable electricity. It would be nice if that was the solution to the problem. But a lot of these heavy industries aren't really compatible with simply just converting them over to renewable electricity. And I've listed 4 of the key challenges here. So first of all, they can't easily be converted because one of the key reasons is that heat is the issue here. So for primary industry, it's normally heat that they're trying to raise, which is why simply by replacing it with electricity, costs go up, and then we don't get so much economic sustainability. The next one is normally, and especially in steel making, we need some kind of a chemical reductant in the process. It's not just about heat or about energy or motive power. It's actually about providing that chemical feedstock in order for the process to actually work. So how we normally do that in ironmaking, of course, is by the injection of coke, which comes from coal, which, as we all know, is highly carbon intensive. So the next one that I think is of interest is that where there is a need for chemical feedstocks, they tend to come from vectors that are carbon intensive themselves. So if you're an industry that's manufacturing a chemical product, for example, you're going to need some primary product to get in there, and it could be as simple as kerosene, but you'll need to get that from a non-carbon intensive vector, which is where part of the problem is. And then finally, which is what I'll go on to in the subsequent slides, is resilience against demand management. So for those of you that work in heavy industry, you know what triads are, and you know that they can have a huge impact on the way you do business. So what we're looking for is a solution that gives us dispatchable energy, but with low negative or possibly, zero or possibly even negative carbon. So let's start off with looking at this issue of dispatchable power. So if we consider renewable energy, and of course, renewable energy is a good thing, and renewable energy comes with its own problems. So I'm going to give you an example here of electricity generation. This is a tweet that was put out in 2017, but it's probably more so relevant today than in 2017, where national grids were tweeting that their primary sources of energy at that particular time, I think you can see the timestamp on there, it's around about 3 p.m. on June the 7th. The primary source of electricity in the United Kingdom was more renewable than anything else, than non-renewable sources. And that's a fantastic achievement for that to happen. But actually, let's look what happens if you follow the subsequent time frame to look at what happens in the hours afterwards. Well, the sun sort of went down and the wind stopped blowing so much. So they then had to turn to gas turbines in order to support the grid. So what I'm trying to say here is that we need dispatchable power in the future. It's likely to be gas turbine based, but that source of power needs to be low carbon. It can't be a carbon intensive source. So that's putting pressure on gas turbine systems to use substances like hydrogen or ammonia or some engineered product that's come from a low or negative carbon source in order to fill the gaps, in order to keep a dispatchable, flexible, robust power generating system, especially in industry, because you have issues such as demand side management. So how's that going to pan out? Well, let's take an example of a gas turbine, which is the research area in which I work. So I've drawn us a graph here of the amount of hydrogen that's present in the fuel versus the amount of specific energy. And really what I'm saying in there, that's like the calorific value of the fuel itself. So you can see that there's quite a spectrum now, which a very expensive asset like a gas turbine is going to struggle in terms of flexibility. And I can give you a good enough example, which is you wouldn't put diesel in a petrol car or vice versa, because you know that the engine isn't necessarily compatible. It certainly isn't compatible with switching fuels. And in gas turbines, the big push at the moment for research, which is why it's a fantastic area to work in, is to look at how we can get flexibility as we start to add in these interesting, extremely variable fuels. It's one thing to develop an engine that works 100% on hydrogen, but the real challenge, the holy grail, is a flexible engine that can work across a spectrum of fuels. So this is what we do in the Gas Turbine Research Centre in Cardiff University. So if we look at the top left-hand image, you can see what we've got is a constant volume bomb reactor. And what we do with that is we put in the fuel mix that we're interested in. It could be ammonia, it could be a hydrogen methane mix. And we look to see fundamentally how that material behaves. Once we've got an understanding of its capability and the burning velocity or the heat release rate, calorific value, that sort of thing of the fuel, we can then move along in terms of scale. So next we go into our high pressure counterflow burner. We look at the aerodynamics of the flame, and then on into our high pressure optical burner, where we look at the stabilization of a swirl flame. And this could be an industrial swirl flame. It could be an OEM gas turbine flame. It depends on what we're interested in. And from there, we can look at modeling, and we can publish work and feedback into the industrial space, what the impact of using, say, methane cut with hydrogen or perhaps different types of renewable alcohols or something like that has been produced. So this is how we have an impact, and this is where the areas of interest are. But what does that mean in terms of the future? Well, from what we've published and what we can see, it's really going to depend on advanced manufacturing techniques. So we've got two concept burners there. One's from Siemens, the other's from GE. And then in the left of the image, these are burners which we've 3D printed out of high temperature alloys in conjunction with some of our industrial partners, including Hywel, which are an additive manufacturing company based in Bristol. And what you'll need for the solution to this flexibility problem, and there's a lot of solutions coming out now, it's normally very complex geometries that can deal with these fast burning fuels. And this is where the action is for us, is producing these very complicated shapes and then managing to test them in our rig. So if we look at some of the industrial impacts, there's the Hy4Heat project, which GTRC have been involved with, where we've been in advising this consortium in terms of what's going to happen for gas turbines and for industrial heat if we start to add more and more hydrogen into the grid, which is a definite possibility when it comes to decarbonisation. When electricity is abundant, you then produce hydrogen, which then goes into the grid, or it could be produced via natural gas cracking with carbon capture and storage. All right, so moving on to the other part of my talk, I said I was going to talk about alternative reductants from renewable sources, but let's actually keep on the hydrogen theme here and look at what's likely to happen in terms of ironmaking. Now, these are processes which are being developed and in places used all over the world. We've probably heard of electric arc furnaces, but in terms of trying to feed electric arc furnaces with primary products that are low carbon, we're probably going to be looking at things like direct reduction using hydrogen. So rather than having coke as a primary input to the process, we would be using hydrogen, which has been produced renewably or with carbon capture and storage, such that the iron is then pulled out of the ore using hydrogen rather than what essentially is carbon monoxide in a blast furnace or a carbon-based process. These are things which are in development. They've got huge potential to reduce the CO2 when it comes to iron making, but there's lots of work that needs doing. So I'll show you some examples of some of the things that we're interested in. The technology routes you'll probably recognize on the left there. We've got a blast furnace. You might recognize it from a textbook, or perhaps it's something closer to you in terms of the area you work in. traditionally fired with coke, which is manufactured from coal, again, very carbon intensive. So then as we start to look at different processes like smelting or direct reduction, there's real potential here for putting in materials which have a lower carbon life cycle and allow for a circular economy to be used. There's also the electric arc furnace, which relies on recycling of material, but you can't really recycle steel infinitely, so there always needs to be some primary input. And this I think, is where the interest from UK PLC is do we go along the lines of recycling, or do we still need some kind of reduced iron process? If that's the case, then we're looking either at renewable fuels, low carbon fuels, or directly from hydrogen. Okay, so this is something we've been looking at this with my colleague Julian Steer, and we've been looking to see whether or not waste plastics can be used as a reductant in the iron making process. Now, we've all heard about the modern controversies with sending plastics away to supposedly be recycled all across the world, only to see them washing up on beaches. And this idea of injecting really low-grade plastic that's never going to be recycled into processes like blast furnaces or for direct reduction is of real interest to the industry, provided they're non-chlorinated, of course. So you can see this is an example of the material. It represents huge savings. I'll just show you what it typically looks like. Hopefully you'll see the video in the next slide here. So what we've got, these are actually two. This is the same kind of coal, but it's just been machined to different sizes. But actually, this is a very good analogy for what happens when you put high hydrogen or high volatile material into a process such as a blast furnace or a high temperature petrochemical process. So on the left, we've got very nicely behaved material that's going through the heating process, heating up nicely, and it's starting to chemically react. But on the right, if you can see that, you're treated to something more like a fireworks display where the material is actually fracturing and splitting apart before it starts to react. You can have problems with dusts being formed in processes like this, or very unstable chemistry. Now, this, again, from an academic point of view, this is fantastic because it gives us good industrial impact for fundamental research that we like doing in the lab. So I'm just going to finish now on describing the CBT, which we have at Cardiff. There are also other CBTs are available. I don't know if Dave's going to talk about them in Swansea later on, but this is a collaboration between Cardiff, Sheffield, and Nottingham. This is where we can provide high caliber doctoral students into industrial challenges, whereby they can work directly with the industrial partners whilst at the same time doing research on low carbon. But in particular, we're looking at resilient decarbonized energy for this, so essentially keeping the lights on. The research challenge is chosen by the industrial partner, and this is very, very good value for money, if you don't mind me giving you the hard sell for a second, for industrial partners to get good people on board and look at these modern processes and modern problems, as well as getting some good training. All right, so to summarize, rather than using words, I'm actually going to use a picture. So hopefully this should be familiar, because this is a diagram of the South Wales Industrial Cluster. This is where I see the collaborative work between universities and industries going in the future, which is where everything comes together for an integrated approach to resilient low carbon energy and primary manufacture. So this will involve either hydrogen or ammonia or low carbon fuels in a fully integrated network with CO2. And if you do your homework properly, you can turn CO2 into an opportunity, not just into a problem, whereby renewable energy, carbon capture, and renewable fuels are being used in conjunction, such that each industry is potentially feeding into the rest. I think this is where the future is going to be. And it's a great opportunity for us to work with industry and do some high impact stuff. Okay, thanks very much. I'm going to hand back to you, John. That's me done. John, you're on mute.
Oh dear, someone had to do that. Okay, thanks, Richard. And fascinating. I'd encourage anyone in the audience to. So Richard's talked to us about hydrogen and the role of hydrogen or alternative fuels for dispatchable power in gas turbines, the potential alternative reductants, and also the Centre for Doctoral Training. So any questions from the audience on any of those issues, we'd welcome, and we'll try and capture those for the end. Okay, so if I can now share my screen again. Okay, so we're going to move on to my colleague, Professor Alan Guwy, who will introduce himself. In fact, Alan and I will do a bit of a double act. I didn't introduce myself at the start, so I'm the Director of the University of South Wales Hydrogen R&D Centre, and I'm also the academic lead for the South Wales Industrial Cluster. So we'll say a little bit more about that, but I'll pass to Alan, and then Chris, if you'll allow us, we'll do a bit of a double act on this session.
Good afternoon, everyone. Just wait for the plane to go overhead. John, can you put up the next slide? So I'm just going to tell you a little bit about the Sustainable Environment Research Centre. I'm Professor Alan Guwy, and I head up the centre. The team is a multidiscipline team. It covers all sorts of research areas that are really applicable to the decarbonisation agenda. And the team has a lot of industrial as well as academic experience, and focusing on the major energy and environmental research and development challenges facing us in the next 20, 30, 40 years. We have an emphasis on doing applied research and development, and we cover areas not just of energy, but waste and water. And actually the interfaces between those are particularly interesting, both academically and industrially, I would suggest. We have facilities at our main campus up in Pontypridd. So on the right hand side there you see the colourful building. That's our main laboratories, where we have more than 14 dedicated laboratories working on all sorts of different areas, including the ones that we'll be talking about today. And then on the left you'll see the Hydrogen Research Centre, and that centre was commissioned and opened back in 2008, and it was the first of its type in the UK, producing renewable hydrogen from PV. And there you see John in front of two Hyundai hydrogen fuel cell cars that we've been refueling for some time now. And we have a broad church of funding, both European and UK, and international funding, and we're lucky enough to be involved in these collaborative projects that John mentioned, Flexus, RICE, and shortly others that will be very significant to us and Wales in the future. So that's a bit about the centre, so I'll hand back to John.
Thanks, Alan. And by now, hopefully, you'll all be familiar with the South Wales Industrial Cluster, and because Costain did a very nice map, and in fact this is version 2 of that map for the deployment project. I'm showing it again, but I just want to emphasise the fact that the South Wales Industrial Cluster grew out of work that was conducted on Flexus, and in response to the call from UK government to try and mobilise clusters. The scale with which most of you will now be familiar if you've listened in during the day, but effectively the prize here is 16 million tonnes of CO2 a year, and that's about that's split between power generation and industry. But it's a significant total, and we're aiming for net zero, preferably by 2040, or certainly in the decade 2040 to 2050. And the work that we're doing academically to support that at the moment is via the Cluster Plan project and via the deployment project, which are UK government so-called industrial decarbonisation challenge projects, but also through a number of spin-off projects, and there's a couple of those running through the Transforming Foundation Industries programme, which are also relevant. So we're actively engaged in supporting the South Wales Industrial Cluster, and I guess the way that I would put it is that we're sort of trying to engage in this idea of active knowledge sharing, and in that case, the core of this is the industrial partners, and their need to look at decarbonising their activity but maintaining competitiveness, and we as academic partners are supporting that. alongside that, there's government engagement at different levels, whether that's UK, Welsh government, or indeed local authority. And there's active engagement at all three of those. And clearly there's a high level of interaction between each of those. So effectively what we're trying to do through both the cluster plan and deployment projects, and then spinning out activity from that, is to identify the R&D needs of industry partners and to initiate solutions to that. And at the same time, the South Wales Industrial Cluster Programme, is to identify the skills and training needs solutions, and that really is at all levels, whether it be the sort of doctoral training type approach that Richard's talked about, and I'm sure Dave will mention as well, elements of that. But it also engages bachelor's level, but it's also with partner FE colleges looking at apprenticeships, traineeships, returners to work, or continuing professional development. So there's skills and training development needs at all levels in that sense. In terms of policy engagement, that's a two-way street. Again, it's about interpreting policy and ensuring that we can react to policy, but more than that, to try and shape policy. So that's active engagement in a number of government advisory boards and the like, and all of the universities that are on this afternoon are involved in that. So in terms of our research, development and innovation projects, we'll say a little bit more about IDRIC. There's a common theme of Flexis, and we'll run through this, and also the spin-off Flexis app project, or also the reduced industrial carbon emissions project. And essentially, I guess what I'm saying here is that we're acting as a bridge to not just the three universities here, but both national and international collaborations, and fostering new collaborations to try and meet those industry needs. And as I say, on the skills side, that's also linking with regional FE colleges, and in many cases there are formal partnerships already existing on that front. Bear in mind, of course, that industry is, although it may have local operation, in many cases this is headquartered overseas. But the core, as I say, is about engaging with industrial partners. That may be through trade bodies as well as the individual industry. And there may well be skills and standards organisations that we're involved with, as well as the legal and financial element here. On the government side, or beyond that, there's, as well as the South Wales cluster, there's sharing knowledge nationally with other clusters, and that's an active part that's being developed, as well as this idea of government expert groups, and particularly on carbon capture and use, and on hydrogen, we've got representation from South Wales within UK government groups on that side. I certainly, last but definitely not least, is this idea of community engagement with the whole decarbonisation agenda. And I guess the key thing here is about building trust with industry and reducing risk. I mentioned IDRIC. So IDRIC is the Industrial Decarbonisation Research and Innovation Centre, and led by Mercedes up at Heriot Watt, who is the UK RI Industrial Decarbonisation Champion. But essentially what IDRIC is trying to do is to foster world-leading high-impact research in decarbonisation, and act as the sort of focal point for national activities on industrial decarbonisation. It's promoting challenge-led research and nurturing talent and building capacity. And very much the idea is that this is still in support, or remains strongly in support of energy policy in that sense. So moreover, there is this idea of challenge-led theme development, and what IDRIC is doing is looking to foster multidisciplinary research, so not just technology, but also to impact on policy, on economics and regulation, so hard and soft science, engineering, etc. Very strong industrial input to this, so guided by industry in the way that I've mentioned already, and also looking to be agile and flexible to respond to the research challenges that the industrial clusters face, and to try and ensure that there's knowledge exchange across and to sort of facilitate this knowledge exchange across platforms to maximise impact. And through all of this, to deliver long-lasting economic growth, decarbonisation, societal benefits, and to build foundation for industrial clusters. And we'll hopefully be announcing that a series of research projects will be starting across South Wales from the 1st of next month, and we'll watch this space on that element. I'm just going to give very briefly a couple of examples from some of the projects of how we're having impact on industrial decarbonisation. And in this case, I'm sort of focusing on electrolysis and PEM electrolysis particularly. So University of South Wales is involved in research on both alkaline, PEM, proton exchange membrane, and solid oxide electrolysis. And guiding this is the potential UK electrolytic hydrogen demand of up to 30 terawatt hours by 2035, or a capacity of 3.8 gigawatts of electrical equivalent of hydrogen made by electrolysis. So I'm just sort of casting back through previous research work and through Flexis, working with industrial partners, including people at ITM Power. And with ITM, we established actually their first commercial sale of a PEM electrolyzer a decade ago. But I guess what I'm trying to point out here is that over that decade, there's been a 2,000-fold scale increase in the deployment of PEM electrolyzers. So from a 12 kilowatt electrolyzer back in 2011 now to 24 megawatt installation coming up this year. And with that, of course, economies of scale, cost reduction, and capital cost reduction. But the key is not just about capital cost reduction; it's about flexible response to the electricity sector and understanding how the economics of that will work in future. All of that's work that we've done within the Flexis program and will continue to do in support of industry and green hydrogen production. Different example here, again focusing on the steel sector, in this case through the RICE project. We've been looking at hydrogen recovery from steelworks gases, and essentially the prize here is that hydrogen from existing steelmaking processes, there's a significant volume of very low cost hydrogen available from steelmaking. But of course, if you can capture the CO2 and either store it or use it, then potentially you've got a low carbon intensity, low cost hydrogen available. So our work in this case through the RICE project has looked at advanced water gas shift processes, standard PSA, but then looking at more novel electrochemical fine purification and compression, so that we can get to sort of fuel cell grade hydrogen purities. And our approach has included modelling, but then you can also see the embodiment that we've got in a pilot scale rig here at Baglan that looks at testing this approach, and that platform we can use for developing in future. So I'm going to switch to Alan now. Hopefully we're not taking up too much time. But Alan, I'm going to switch to you now, if that's okay.
Thanks, John. So following on from that, another one of the projects that we've been developing, I mentioned right at the start that we work across sectors, and water is particularly one that we're interested in. And the water industry is a big consumer of energy. About 2 to 3% of all electricity generated is used in the water industry. And of that, a significant energy, one of the most intensive parts is the wastewater treatment process, which I've been working on for probably 30 years or so. And you can see in the treatment of sewage, the sort of energies used, and about 25% of that is used in aeration. A significant amount is obviously dealt with pumping and mixing. And then there's transporting of sludge. So we've been looking at how we could change the whole flow set to improve energy efficiency. The other thing to say, of course, is that in using all this energy and treating the sewage itself, it's a large emitter of greenhouse gases. About 1% of all of UK's greenhouse gases are emitted from wastewater treatment plants. Next slide, please, John.
Okay.
And you can see this in this standard flow schematic of what a sewage treatment plant is. So on the left-hand side here, at the top left-hand side, you'll see the aeration process where air is pumped into a tank. You've probably flown over them in planes, and you can see the huge sort of football-size tanks. And basically, that's where the biology works, and it's energy intensive to get that air through and mix it. And then what happens is it converts that sewage into about 50%. It's about 50% reduction into effectively another sludge, which is then settled. And then you go through another stage, which is the anaerobic stage, which is just below that in the brown shaded sector. And again, you're using more energy here with thermal hydrolysis to make it more digestible. And then you can regain some of that energy by converting to methane through anaerobic digestion, which I've been working in for more than 30 years. The downside, of course, is that although you're producing energy in the form of methane, you get fugitive emissions. And you see this, we've learned this now over the last 20 years, that actually about 4% of the gas that's produced is actually emitted into the environment. So you have significant issues there with greenhouse fugitive emissions. And across the whole process, you've got CO2, nitrous dioxide, and indeed the transportation of dewatered sludge backwards and forwards to various parts of the process, and then eventually to land. And all of this has emittance of greenhouse gases. So we need to do something to change this whole flow sheet. And that's what we've been looking at. So next slide, please, John. So this is where we talked about the interfaces of where we work with the hydrogen, water, and waste. And we've come up with a process that we've termed oxy-high water. And this really addresses the sort of issue around electrolysis. So we all know about hydrogen being produced in electrolysis, whether through PEM or other types of electrolysis. But the oxygen is usually allowed to just discharge to atmosphere, and that's got value. And actually, what we identified has got significant value if we were to use that in the aeration treatment lane. So there's the photograph on the right there is a traditional aerobic treatment process, which is open to the atmosphere. Lots of air being blown through it, lots of energy, lots of VOCs and greenhouse gases being emitted. So we thought, well, let's use that oxygen and try and improve the efficiency of the process. And in fact, we should be able to reduce the footprint of such tanks, if we put a cap on it, certainly, by 100 times. And then we'd have to work out exactly how much oxygen we would need to do that. Well, we need roughly about 39 kilotons per annum of oxygen to treat Wales as sewage. That would in turn produce nearly 5 kilotons of hydrogen in electrolysis, which we will most likely be doing anyway in the future. And that actually produces enough hydrogen equivalent for 35,000 fuel cell electric vehicles. And that's a revenue of £38 million, not discounting the benefits of the oxygen used in a much more efficient wastewater treatment plant if we can achieve that. So next slide, please, John. And this is the schematic of the pilot plant that we originated the idea in Flexis, and now we have funding through RICE to, I guess, build it to a pilot demonstration phase. This is schematic at the minute, but you'll see the sort of idea that we're going to embody down at Baglands. So the hydrogen that we produce from the photovoltaics on the center roof will generate oxygen and hydrogen from the electrolyzer. The hydrogen can go for refueling, and the oxygen then we will put through a capped bioreactor, where we're recycling this oxygen. We don't need to put air in at all. And so there is none of the wasted emissions. And in fact, if you think about it, you're actually only getting about 1 to 2% solubility of oxygen when you aerate with air. But with oxygen, you can keep it 100% or whatever you wish. And then because it's a sealed bioreactor, we can then, and with much more efficiency, we can use membrane filter systems to extract the treated wastewater and other things in the wastewater that might be of value, such as nitrogen and phosphate and many other things. And so this is the wastewater treatment option that we're going to be looking at in RISE. And the next example, next slide, sorry, John. Through Flexus, we developed a concept called the VFA factory. And this is taking wastes, waste gases, waste biomasses to produce carboxylic acids. And the one highlighted here is funded through the Flexus App project in conjunction with Tata and Welsh Water, where we're actually looking at the separated hydrogen that John was talking about earlier from the steelworks. And of course, that can be used for energy and fuel, but it also can be combined with the CO2, which is also present in the syngas from the steelworks process. And in doing so, we can make these carboxylic acids, or VFAs, and the most significant one of those is acetic acid. And they have a value of around about £300 per tonne, so significant value. And from that, you can make even more valuable compounds, bioplastics, biosurfactants, and so on, and many more. And so acetic acid could actually become a green platform chemical of the future, and it could be sourced through waste gases or waste municipal wastes. Next slide, please, John. And here you'll see the bioreactors that we've, the top photographs are the ones that we have in the lab. And they use electrodialysis to actually extract these valuable VFAs. And the global value of these is around about 1.3 billion already in the world, and it continues to rise at an ever-increasing rate. At the moment, it's around about 12% per annum, but I think this is going to increase significantly as we displace fossil fuel equivalents for green chemicals. And we already have a pilot plant funded through RISE at Tata, looking at actually conversion of carbon monoxide in the waste streams. And we're about to, through Flexus app, place a H2H plant down adjacent to the COACE plant, which makes up part of the VFA factory concept. And if you look at we've done some calculations, and if you look at the value you can get from the blast furnace gas alone, it's in the order of £0.3 billion per annum. So, roughly a quarter of the world market. So there's significant potential for capturing and using this carbon in green platform chemicals in the future. And so that's a flavour of the projects. And again, we just mustn't acknowledge all the fantastic support we've had from the funding bodies, but also the industry, without which we could not do the work. So thank you very much, and back to John.
Thanks very much, Alan. And I'm just going to hand over to Dave, if that's okay. I'll hand straight to you, Dave. That's all right.
No problem. Right, hopefully you guys can see the slides. I can only see the slides and nothing else. So this is the last section here. So I'm just going to summarise some of the work that we're doing at Swansea, also, but link it to the work that you just heard about from both Cardiff and Swansea, and start off by explaining a little bit about where we're going in the future. So. Why have I got these old pictures? Well, my dad took pictures of everything about industry back in ancient times, and also gave me a passion for science and solar power, which has driven my research career. And what we want to see, obviously, is transitioning our industry and society over to a net zero way of operating, which can be a trailblazer for the rest of the world. A lot of our work is, as you've seen from these previous presentations, funded by European Union sources. So one of the things that we're working on now, because we've got 2 years left of that kind of funding, is how we build an architecture that takes us through to 2050. So the first couple of slides I got to explain a little bit about that. And essentially how we bring together the major research hubs in South Wales to provide underpinning research and training support for the industrial cluster and society in general, and how that can connect to our existing innovation pipeline, leading to both demonstration projects, as you've heard about, but also leadership in industrial decarbonisation. And we're talking about power and industry. The picture on the left there is probably the last time we'd be rebuilding fully a blast furnace in South Wales, potentially, although there's some great stuff still to do, as Richard said before, on different fuels. The way we build buildings, I'm a bit passionate about steel, so there's always a bit of steel in those as well. The way we drive cars, both electric and hydrogen, and how we can take that on an international journey, because actually Wales has great links into countries like India and can help them with decarbonisation as well. And Switch Connect is what we've called this idea, and essentially it brings all of our projects like Flexus and so on and so forth together. So this is a kind of pictogram that describes where we see we're going. We're bringing the gas turbine centre, the Flexus project that you've heard about, the aspects of Alan and John's research on hydrogen, together with projects that I'm just about to talk to you about, Specific and Sustain, all with a view to supporting both societal and industrial decarbonisation, and in many ways to make sure that we've got those teams of people who are already present in Wales doing great work, supported through the delivery process, so that we're actually, using the talent we've got now, and as Alan and John both mentioned, and Richard as well, growing the next generation of talent. So I'm gonna take you through some examples which are slightly different on 3 projects at Swansea, which are linked. So some stuff on Specific, a little bit on Sustain, and some work we're also doing on Flexus related to industrial decarbonisation. And then I'll also say a few words linking in with what Richard was talking about in terms of training provision and skills, because without people on the ground, both those that we have now, with some level of retraining and new people into the future, we can have all the technology we want, but we won't have a successful industry. So what does Specific do? Hopefully these videos work. If they don't panic. There's nothing hugely significant there. But what we've got in Specific is an innovation and knowledge centre funded by UKRI, via EPSRC and also European Union funding, which is developing materials to generate, store and release energy. So both solar panels, new kind of printed solar panels, and different types of printed battery technologies, and release technologies that can release both heat and light, mainly for the use in buildings at this point, but clearly the processes that we've got are equally applicable for making other materials, like for example electrodes for hydrogen evolution from water. And the image of the 2 guys on the bottom right there, that's right, yeah, unfurling is in Newport now. There's a factory been set up by our colleagues in BIPVCO that are actually taking this technology, manufacturing it in Wales, and then integrating it into, in this case, steel roofing. But as you can see, the membrane material could be laminated onto any kind of roofing product. Why am I showing you this sort of stuff? Well, actually, for industrial decarbonisation, you've got some of the most exciting areas for this kind of technology, because you've got very, very large buildings. So as well as looking at the technologies of printing and coating of solar panels and so on and so forth. We're looking at how we can demonstrate that on real buildings. So the video in the top left is of us building our first active building, the classroom, which had a sort of 17 kilowatt peak solar roof, first of its kind, with electrical storage. It's also got solar thermal collectors on there generating hot air, which reduce the requirements for energy on a heat pump. But this was designed as quite an innovative building with multiple different technologies on it. But what's been really interesting about this is how well it's worked as an experiment, and how we're now able to deploy these same sorts of buildings as classroom demonstrators in countries like India, in rural applications where there are no grid connections. The building behind the classroom, the sort of curved roofed office there, that was was a modular build. That's got a much bigger PV roof and has different types of electrical storage in it. We've got flow batteries in the one building. We've got traditional lithium batteries in the other. What that's aiming to show is that the office building of the future, supposing there is such a thing, of course, is actually something that can generate power. And that's been powering my Nissan Leaf for the last 28,000 miles. Not so much recently, clearly, because I sit on my Zoom chair and save carbon by not going to work. So that's another way of thinking about things. But if we think about our factories, the images on the bottom right there, a big distribution centre, ideal for covering in PV, including storage, considering hydrogen vectors, as John and Alan are doing down in Baglan. And the building in the middle there that looks a bit like a rusty shed, it is. It's an old steel building. We put a big solar thermal collector on it. That whole wall there is a solar thermal collector. And that heats the building year round, and we've not used any gas there for the last 9 years, right? And it works very, very well as a technology, and is a way of industrial groups actually thinking about their property not as an energy using element, but something that can actually generate power, and then using that power on site. Clearly, we're taking this to work overseas with support from UKRI in India, also in Mexico. The top right, some Mexican T-shirt printers looking a little bit confused, making solar cells, and also working in African nations, particularly in terms of bringing educational aspects of how to make low-cost solar work in those environments. But as a technology, it has global potential. So as part of Flexis and as part of the IDRIC project that John also mentioned, slightly moody picture of Port Talbot there with a message from God about blast furnaces, I think. But what we're doing there is adapting some of the technology that we've used for solar thermal collection, which is a kind of version of vermiculite that's got a salt on it, which I'll tell you about in a minute, and using that as a heat store to create mobile heat energy. So again, thinking about waste that would normally be thrown away into the sky, waste energy, and how you can use that potentially to create heating in buildings. Recognizing that about 30 to 40% of our carbon emissions in the UK come from heating buildings. It's a very simple process that's been developed by our team. They use this vermiculite material with a bit of calcium chloride on. The calcium chloride is a salt that allows water on and off of it. You dry it using hot air, either from a solar collector or from industrial sources, and then that heat energy is trapped on the matrix until you expose it to moist conditions again. So it will store heat pretty much indefinitely. And that large box on the top right there is a unit that we've put into that shed I showed you on the previous slide. And we use that for interseasonal heat storage. So that container vessel has a ton and a bit of this material in, and that can provide heating for around about a month during the winter months. when there is less solar thermal available. But imagine how now we can use that same material in kind of bags transported around for home heating and charged up using industrial waste. That's another axis that we're looking at. So the third project I was going to mention is our Sustain Manufacturing Hub. This is very much steel focused because it's actually all about the future of the steel industry. It's a collaboration here with the universities in Wales, but also with Warwick, Sheffield, Durham and UCL. And it links into a collection of the innovation assets in the UK, be that specific, I've already mentioned, but then in other of the universities, you've got WMG, you've got the Royce Institute and so on, bringing industrial questions from the steel industry, from the 5 UK steel companies, and trying to answer them and push technology through from the lab into the factory. And in essence, what we do is go all the way from the grand challenge of carbon neutral iron and steel making. So some of the work that Richard spoke about that Julian's doing in Cardiff with Peter Holloman at Swansea, is feeding in there on using different waste materials as a carbon source. We're looking also at carbon capture and conversion, clearly, but also increasingly on how we can improve the quality of scrap, so that some of the issues of increased use of electric arc furnaces are not as problematical for strip steel as they would be if you just take scrap as it comes in. In the UK, we produce 10 million tonnes of scrap a year, and our current iron and steel production rates are about 8 million tonnes. So we've got an excess of scrap, which could be useful for us if we can explore more use of that in making new products. Sustain moves across areas of data-driven innovation. That's driven by work in Warwick. And then also thinking about how we use lower energy production routes. And that also links for things like different kinds of heating techniques. So, for example, some of the heating techniques that we use, which are electrical, like near-infrared heating, those are much more efficient because they only apply heat to a component while a light is switched on, as opposed to a gas jet that produces power or uses power all of the time. And then all the way through into new products that will be the underpinnings of aircraft, the electric and hydrogen vehicles, the rolling stock, the sort of rails for HS2 and so on, and even into power sources, such as the SMR, and hydrogen power sources that we will need in the future. Not forgetting really prosaic things like metal food packaging, really useful use of steel, but one that requires really high quality steel to make it actually work, because some of the packaging materials are only 100 microns thin. So a little bit about training and skills. This will be the last bit that I talk about. We've been working with the industry in Wales for quite some time, well, since '92 actually, on a kind of doctoral training activity. And it's morphed over the years into something more of a training academy, which looks at doctorates, it looks at standard degrees, it goes all the way down into work-based learning, and has been very successful for supporting talent growth in our industrial cluster and beyond. There's some stats which I will just jump through actually, because I don't think there's enough time really to talk about those. And where we're going with this now is to take the concept to create a kind of switch on skills academy, which has a variety of skill steps, a little bit like what Alan was talking about before, where our universities work together on all the way from high-level skills like postgraduate development and doctoral training through apprenticeships and work-based learning to retrain staff, all the way down into community activities and outreach in the schools. And I think this is really important, because actually it is actually going to allow people to develop their careers without any barriers, and they can change their careers at any point. And I think that's all I had to say. Hopefully Switch Connect will start taking shape and joining together all these projects. and it's going to be a very exciting 10 or 15 years ahead as we try to lead the UK into a net zero and decarbonised society without actually deindustrialising. So thank you very much for listening to us, and I'll stop sharing at this point.
Thanks very much. I think we've got permission to run on for a few minutes. So I think there's a drop dead at 10 past. So if we're still talking at that point, we'll just get faded out. But I'm going to first address one of the questions that was in the comments box. So Reese, thanks for that. Question is, has anyone put a figure on the economic opportunity hydrogen presents to Wales? And what about the potential cost of losing our early leader position and having to import that tech fuel? I'm going to leap in there first and say that there is a figure. The Hydrogen Task Force put forward a figure of the potential for 150,000 jobs in the UK by 2035 in the hydrogen sector, and an additional GVA figure of something like 35 billion by 2035. So the easiest thing to do would just be to do a Barnett formula on that. But on the other hand, what we've just been talking about is that Wales is heavily industrialised. South Wales particularly is heavily industrialised. Our economy relies on that. And one of the significant ways out of our current carbon emissions is about adoption of hydrogen technologies. So from that point of view, I would say that we have, you skew that figure quite significantly. You can do the maths in terms of population, but there are a massive number of jobs potential, and there's a significant economic value of the transition to hydrogen. But as we've seen with other transitions, early mover advantage can be lost if we simply import technology and we don't look at manufacturing new technologies in the region. So we're still, and the world is still at an early stage of this, but it's moving very, very rapidly, and a number of the advantages that we have here we should put to the advantage of Wales. Does anyone else have a view on that, or particularly on early adoption and how we can harness the opportunities?
I'll just say something very quick, which I think is the opportunity is there not just for hydrogen, but all of the other non-fossil based fuels. So what Richard was talking about in terms of solving waste problems by using, a blast furnace. Great idea, right? Because otherwise that stuff's going to end up in the ground, because there isn't anything you can do with that kind of fluff that ends up that no one wants to recycle, right? Likewise, if we've got a very positive attitude towards renewable and SMR and other nuclear power sources in Wales, we can be a little bit more like Norway is in terms of, embracing all of the new technologies that are non-fossil fuel based. And I think it's just a tremendous opportunity for a new industrial revolution to start here. Just imagine what our work can do around the world when it's deployed in countries like India, for example, where there's lots more solar resource and things like that. But they're at a kind of junction at the moment where they can go fossil, non-fossil, and we need to try and keep them on the I think I pointed the wrong way there because I'm looking at myself in the wrong way, but we need them to go in the non-fossil direction. Yeah.
Well, that's great. Alan or Richard, any other views on that idea of the potential economic benefit of acting on the technologies and translating what we're doing as academics into the real world?
Yeah, I mean, I think you both coined it pretty well. There is an opportunity here, and but there's been an opportunity for a while, and we do need to start acting fairly quickly, I think. And I think that's why the partnership we have with the industry across Wales is absolutely pivotal. And there are some low-hanging fruit that we can take advantage of. And we have the expertise and skill sets within the region, and we need to capitalize on that. and grow it. And as Dave says, we can make a new sort of revolution here. And I think there are solutions. I was listening to the news at lunchtime today. The question is how. We don't have to make the case anymore. We just have to make solutions, come up with solutions, and start providing them. And they're quite straightforward. We just have to get on with it, and we can support the industry with ongoing ideas and research to enable that supply chain of ideas to make money for the industry, but also for our population, and hopefully, as David said, sort of spread that as we've done in the past, and we're still doing across in lots of different sectors and scientific research across the world. So we improve the chances for the whole planet, not just South Wales.
Richard.
I think there's a global competitiveness issue here that hasn't raised its head yet. A good example of this is our relationship with the Chinese steel economy. So if you look at some of the problems that we've had trying to sell primary steel, where you have countries overseas that can make it cheaper, is that the problem becomes politicized when those countries start to dump cheap steel onto the market. Now imagine what it would look like if those countries were dumping cheap, sustainable steel onto the market. You suddenly run out of cards to play. You can't go to the government and say, we need some political pressure to stop somebody on the other side of the world selling this steel, if it turns out that steel has a far lower carbon intensity than the steel you're making in this country. That's pretty much the end of the game, because you're not going to win on economics, and you're not going to win on trying to sell a product that's worse for the environment, when countries such as the UK are signing up to Paris climate change agreements and future protocols from beyond that. So the time to act is certainly now, but it may manifest itself in a way that we don't appreciate yet. We may be thinking that it's about climate change, but it could actually come down to economics that we haven't anticipated. And it's not as if those places are doing nothing on carbon capture in terms of large industrial research, because they are. And you just have to go online to look at the amount of research that's being done in places like China in comparison to the UK.
I'm very conscious that we risk being faded out here, but I just wondered if perhaps, Dave, if I can throw back to you for any sort of closing comments, particularly around how we might continue to collaborate, work together, both as academics and with industry.
Yeah, I mean, I think, the assets that we built up during the time period where we've had European Union funding have been fantastic, right? And I think that puts our region at a particular strength compared to other areas. And it's particularly unique that the assets and the industry are in the same place. So, my view really is, if we get everybody in the same place and we're all talking to each other and we're actually pointing in the same direction, it's all ours to play for, and therefore a very positive opportunity for decarbonisation, and not something we should be scared of as being something that's just going to mean everyone has to become a wood whittler.
Thanks, and well, on that, I think there's a very positive message that we've worked hard. We can continue to work hard together and use what we've done so far to bring further benefit. So, with that, I'm going to close the session. Say thank you to all of the presenters. Thanks very much for a very interesting session. Thanks especially to the audience as well. Hope you've got some insight, and thanks very much. Okay, thank you. Bye-bye.
Thank you.
Thank you for watching. Rewatch all of our sessions online. Thank you to our partners.